all across the world. Um, I'm working for Fluence and prior to that MFC for now more than 7 years. Um, I'm based now in the US, focusing on the MABR products for industrial and municipal mostly. And I'm really glad to have this webinar with you.
Thank you, Neri. Thank you. And please let me know if you can hear me well. Just raise a note, make a note or anything so I know. But today's webinar, we're not going to take you through everything about MABR. The idea is to kind of provide updates and some news about stuff we've been developing and been in the works for the last few years. I will do a quick 101 as the beginning of this webinar about MABR technology and explain the principles, but I'm intentionally not going to go into great depth on the technology and how it works, because we need to leave time for some of the updates that we want to provide you all. So quickly about MABR, just like many other technologies in our industry, we use acronyms. They all sound very similar, but essentially very different. MABR stands for membrane aerated biofilm reactor, which, if you look at a conventional wastewater treatment process, you will always have your pre-treatment part of the process. You will always have your biological part of the process that needs to be coupled with some sort of a liquid-solid separation mechanism. In this slide, we're using a secondary clarifier as such mechanism. And then depending where you are in the world, you may be required to meet tertiary requirements or higher effluent requirements, which you need to utilize some sort of tertiary filters, followed by some sort of a disinfection. In this example, we're using UV. And then you will always have your excess sludge as your byproduct from the process. This is your typical / conventional way we treat domestic type of wastewater. The MABR is a component that goes into the biological part of the process. And so from now on, for the rest of this introduction to MABR, I will focus on the biological part of the process, and I'd like everyone to assume that all of the equipment around it and all of the processes around it are staying exactly the same to what's been utilized or used in the previous years for many, many years. Okay, so we're only talking about the biological part of the process. Now, MABR essentially is a way to introduce oxygen into the wastewater. So it basically replaces your aeration devices. So this is just a short timeline demonstrating the evolution of aeration. So back in the 50s, we used to have surface aerators. We still see them today. Fluence actually sells them pretty well. These are type of aerators that you put on the top of a basin, where they would spin really fast, and whatever air the wastewater would be able to absorb from the atmospheric air, it would utilize it for the biological process. These mechanisms are very they're being used all over the world, but they're not very efficient when it comes to energy. And then around the 80s, they came up with coarse bubble diffusers, which basically meant instead of introducing the air from the top of the basin, they figured we should introduce it from the bottom of the basin. That did make the process more efficient and reduce the energy consumption associated with aeration by a third, down to approximately 2 kilowatt-hour for every kilogram of COD that is being removed. And then they say, well, if we can do coarse bubble diffusers, why not do fine bubble diffusers? Make the air bubble a little more available for the bacteria, and they came up with the fine bubble diffusers, which did make the process more efficient, knocking it down to about approximately 1.5 kilowatt-hour for every kilogram of COD that is being removed. And then in 2015, Fluence came on with the MABR technology, demonstrating it can knock down the energy associated with aeration by over 90%, reducing it down to 0.2 kilowatt hour for every kilogram of COD that is being removed. The way that this is being done is that in our MABR configuration, there are a couple more other ways that we're seeing MABRs being utilized. In Fluence's MABR configuration, we're using flat sheets, which we create a water sleeve out of. So we create a sandwich of a semi-permeable membrane, another semi-permeable membrane, an air spacer in the middle, and a water spacer outside of that sleeve. We weld the circumference of this sleeve in order to come up with this elongated rectangular sleeve, which is again built with that sandwich I showed before. That sleeve is approximately 875 feet long. We push atmospheric air at very low pressure through one end of the sleeve, let it travel for the entire 875 feet long sleeve until it goes out back from the exhaust valve back to the atmosphere. This is not how we're introducing air into the wastewater. This is just to maintain fresh air inside the sleeve 100% of the time. Now, in order to conserve space, what we do, we roll this sleeve up in order to come up with this spirally wounded shaped object on the top right hand of the screen. The reason this is black and that is white is because before we roll it up, we put the water spacer in order to create spaces between one layer of the sleeve to the next one. So now when we have this spiral, we start stacking them up one on top of the other in order to this is a function of how deep the basin that they will go in. This is horizontal because this is how it comes out of the factory, but in reality, this will be inserted vertically into an existing biological basin or a new biological basin based on the depth, and we will elaborate on that in a little bit. But because we're continuously pushing air through one end of the sleeve throughout the entire sleeve, essentially we need to anchor those towers down to the concrete in order to prevent it from floating up. So it's essentially like putting a balloon underneath the water. Now, the way that we're able to introduce the oxygen into the wastewater, not the air, just the oxygen, is, as I described, we're pushing air inside of the sleeve, which is represented by this blue line right here. Air comes in, air goes out back to the atmosphere. This semi-permeable membrane allows air to diffuse out of it and not let water flow into it. It's a matter of surface tension and some coating that we put on that membrane in order to make the oxygen transfer more efficient. The reason oxygen would transfer into the wastewater is because we are creating an oxygen concentration difference. In the air that we push inside the sleeve, again represented by the blue line, we're using atmospheric air that has approximately 20% oxygen concentration inside of it. And this MABR tower is going to be submerged in a tank full of wastewater. Underneath the wastewater, you have bacteria that starts to develop, utilizing whatever oxygen is available in the reactor, depleting the dissolved oxygen in the biological reactor almost to 0 milligrams per liter. That air oxygen concentration difference between inside the sleeve, 20%, to the biological reactor this sleeve is submerged in, 0% is the driving force for oxygen to diffuse from the high concentration side through the semi-permeable membrane to the low concentration side, the wastewater. And the nice thing about diffusion is that it's an effortless process that consumes no energy. And that is how we are able to reduce the energy consumption associated with aeration by 90% compared to fine bubble diffusers, where we're just pushing air at the bottom of the basin. Okay, now beyond just being a very, very efficient diffuser, as you can imagine, this sleeve is a great platform for bacteria to develop on top of it in a form of a biofilm. Okay, and unlike MBRs, which MABR resembles by its acronym, this is not a screening membrane. And unlike MBRs, is trying to do anything it can in order to avoid, quote, biofouling, we actually promote the growth of bacteria on top of the membrane, because this is what is going to act as our treatment capacity. So essentially what is happening, and at this time, the dashed line right here, the white dashed line represent our semi-permeable membrane. As I explained before, we're pushing air into the screen, and only oxygen is diffused perpendicular to the direction that we're pushing the air from through the semi-permeable membrane into the wastewater. Okay, adjacent to the semi-permeable membrane from the wastewater side, that is where we have the bacteria that love oxygen the most, because this is where oxygen comes from. And it is using the ammonia in the wastewater in order to convert it into nitrate. The nice thing about this bacteria is that it's an autotrophic bacteria that never becomes very thick. So while it is still a biofilm, it's a biofilm that never exceeds more than 100 microns in thickness. Okay, and that biofilm covers the entire surface of the membrane, and essentially resulting in depleting all of the oxygen that we worked so hard to introduce into the biological reactor, creating an anoxic volume behind the biofilm. So if you were to ever take a DO probe and to dip it in an MABR, in a reactor powered by the MABR technology, you would actually get anoxic readings. The only aerobic place is adjacent to the membrane wall and the aerobic biofilm. These anoxic conditions enable the development of a second type of bacteria, this time anoxic bacteria, that is able to utilize the nitrate that the autotrophic bacteria converted from ammonia, and utilize the BOD that exists in the wastewater as a carbon source and complete the nitrogen removal process by denitrifying the nitrate into nitrogen gas. So essentially, this technology, beyond just being a very efficient diffuser, it enables a simultaneous process of nitrification and denitrification without the need to have two separate basins, an anoxic one and an aerobic one, and without the need to have an internal nitrate circulation. So again, to just clarify this very, very clearly, we are not using the membrane as a filtering mechanism. The MABR membrane is not a physical barrier. It's just a component that is submerged in a tank in the biological reactor, allows oxygen to diffuse through it. So that is the only thing that passes through the membrane and allows the growth of biofilm on top of it. Okay, it is very different than a filtering membrane that I'm demonstrating on the left-hand side, which needs to withstand very high pressures and constantly get cleaned and so on. So these two, we're using the same word membrane, but the function of the membrane is very different between, call it an MBR process or a UF membrane, to an MABR process, which acts as an aeration mechanism. So hopefully that quick review of the MABR technology is relatively clear. And hopefully most of the people who attend this webinar are already familiar to some extent with the MABR technology. But as I'm referring to it, MABR is a technology, it's not a product. So what Fluence had done, we've taken the technology, which is represented in the center of the screen, and we've created multiple products around that technology. In today's webinar, we will focus on the Aspiral Flex product, and later on, Neri will discuss our SUBRE product and some updates associated with it. Talking specifically about the Aspiral Flex, this is where we have created a package plant product line powered by the MABR technology. And the approach that we've taken about it, we call this product line Aspiral Flex, and we call it the building block approach. So the idea behind it is that we've decided to develop our package plant in building blocks who have the same dimensions, looks, and sizes as typical marine shipping containers. These are not refurbished shipping containers. These are water tanks that we build from scratch, but we build them in the same shapes and looks and dimensions as marine shipping containers, and we actually certify them as such. One of the things that we have learned through the pandemic and through everything that has been going on in the world in the last 5 years is that the logistical component of any infrastructural project is taking more and more volume in terms of budget out of an overall project price. Okay, and if you're able to reduce that logistical component, you are able to reduce the overall price of an entire project. And this reduction is becoming more and more significant as we move forward in life and in the world and everything that's been going on. So having a building block that is for a general contractor is the same as a marine shipping container alleviates a lot of concerns of how do you move it from one place to another, how do you transport it, how do you ship it, how do you install it, how do you lift it. All of these things are very straightforward because a general contractor would address this just as a conventional shipping container that would have four locations to lift it and to install it and to offload it wherever it needs. Additionally, um, building everything in such a block helps us design everything in advance and pre-test everything in our factory. And so minimizing the labor associated with the installation on the field has been reduced quite significantly compared to other typical package plans. Because another aspect that we've seen is that labor is also a very expensive component. And so if we're able to reduce the amount of labor that is being dedicated to installing these package plans, again, we're reducing the amount of overall price for the entire project. And so those were some of the drivers that led us to develop this building block approach. So what is that building block approach? As I mentioned, all of these are in the shade, all of our building blocks, you need to review it as Lego. In WEFTEC, I actually brought Duplos with me to try and demonstrate this. But essentially, you need to review this as Lego bricks. And every brick would have a different color and a different size and would have a different function. So for example, a few of the Lego blocks that Fluence has are Lego blocks that are standalone biological reactors. We call these Aspiral Ls, L for large. And in each biological reactor, you can install up to 5 MABR towers. Okay, so in this example on the left-hand side of the corner, we're seeing an Aspiral L, which is a standalone biological reactor that would have 3 MABR towers installed in it. The remaining open volume will be utilized by fine bubble diffusers. We are always promoting a hybrid process. Neri will speak a little more about that in his part of the presentation, but for the sake of the discussion, this is what we would refer to as an Aspiral L3. And this is a standalone biological reactor. So obviously a standalone biological reactor cannot do much, right? But once we couple it with example, an Aspiral MBR container, this is our standalone MBR container, which has UF membranes inside. It would have all the chemical dosing, all the blowers that you would need for air scouring, the control panel that control the entire plant. And so when you couple a couple of Aspiral L units with an Aspiral MBR, all of a sudden you have your package plant. This would also include the pre-treatment. It would include, when I say this, I'm referring to the Aspiral MBR container. It would include the all the dosing pumps, all of the disinfection mechanism, whether UV or chlorine disinfection, and so on. Essentially, each one of these blocks has room to accommodate up to 4 MBR cassettes or UF cassettes. Each cassette is capable of treating up to 50,000 gallons per day, which means that, quick math, a single tank like that can treat up to 200,000 gallons per day of domestic wastewater as the liquid solid separation mechanism. You would obviously need to couple it with a couple of Aspiral L systems in order to get the biological reactor as well. Okay, now let's say an application does not need an MBR. So we have our Aspiral clarifier, for example, which is a similar size container, but inside you would have up to 3 small circular clarifiers. Each clarifier can treat up to 25,000 gallons per day. So 3 such clarifiers would give you a treatment capacity of up to 75,000 gallons per day. It again comes with its pre-treatment. It comes with the disinfection. There is an optional header to put a pressurized media filters to get tertiary treatment effluent quality and disinfection, of course. So again, we are trying to give you to offer multiple types of solutions in order to address the same application based on the drivers of specific application. And that is really the key or the value of the building block approach. Basically, we're not confining our potential clients by saying, look, this is our package, it includes everything, take it or leave it. No, if you already have biological reactor, but what you're missing is some liquid solid separation capacity, we can offer our MBR or our clarifier as standalone. If you already have more than enough liquid solid separation capacity, but what you're missing is only biological volume, we can offer only the standalone biological volume, or obviously we can offer the complete package. So for example, that's how we can start mix and matching our solution based on a specific application and a client's driver. So the first example that I'm showing is coupling one of our Aspiral sludge EQ tanks. So that's again a standalone tank that has a baffle wall. This tank has approximately 17,000 gallons of holding capacity. If we split it into two, which we typically do 12,000 gallons toward the flow equalization and 5,000 towards the sludge holding. We're coupling it with a couple of Aspiral L3 and an Aspiral MBR. Okay, so right here you have a complete package that includes everything from flow equalization, biological treatment, liquid solid separation, disinfection, sludge holding, and of course, all the little pumps, the fine screening, and everything in between. Okay. Another example at the bottom of the screen is if a client already has an existing flow equalization that they can use, or they can repurpose something from their existing facility, and they don't need the flow equalization, and they don't need the sludge holding because they have that. So in that case, we can offer only our standalone biological reactor plus what we call our Aspiral M+ unit, which has some additional biological reactor capacity. It has a small clarifier inside, a media filter inside, and disinfection by chlorine or UV, depends on the preference. All of this is tried to explain some of the flexibility that now Fluence has as a tool due to the building block approach, as I like to call it. So some real life examples, and these are real applications that we can already invite people to see. Lagoon treatment, side stream treatment. In Iowa, we've been working with our good colleagues. I saw Nathan is on the webinar, so good to have you, Nate. Where we're going to polish off or treat a side treatment from a lagoon. So the client had existing lagoon system, 3 lagoons as can be seen, but the problem is that they were not really compliant with their actually BOD TSS due to algae growth in the lagoon in the summer. And we were not sure if it's truly only a BOD TSS issue, because what really happening is the algae grows and then it dies and then it breaks apart, and that's where your BOD and TSS starts to spike up. So we were not sure that just removing the algae will necessarily solve all the problem. Perhaps addressing the cause for the algae to grow would also help with solving the problem. One of the causes for the algae to grow is the building block of an algae, which is carbon and nitrogen and phosphorus. So we're contemplating to say, look, if we remove the nitrogen, perhaps the algae will never grow in the first place. The plant will be meeting its BOD and TSS limits. So this is an example for a project that is actually being executed as we speak. In Iowa, we're using our building block, our M2+ in that case, to treat the lagoon to some extent in order to get it into compliance. And that is obviously much cheaper compared to just canceling the whole lagoon system and putting an advanced treatment in it instead. This is a significantly cheaper solution because you're still utilizing the lagoon as a treatment capacity and an infrastructure that is useful because it's there, instead of just canceling it and putting a whole new system in place. Another example, this is where a client had an existing MBR plant. I'm not going to say the brand because we're only wanting to promote Fluence in this call. And they were basically, the client was interested to increase capacity. So one of the things that we were seeing is that what they truly are missing is only biological volume. In other words, their UF members were big enough in order to support the increase in capacity they wanted to get to. Their fine screen was large enough to accommodate it. So truly, the only thing that was missing was a biological reactor. Everybody else that the client had approached offered to build a new plant to cater for the increasing capacity. What we've done, we said, look, we're seeing that the only thing that you're missing is biological volume, biological capacity. Here is our standalone L3 unit. Couple it with your existing facility, and you'll be able to be in compliance. Obviously, we were about a third of the price compared to everyone else, and that's why the client ended up selecting this approach over others, because it saved them a lot of money. So to summarize and to try and stick to times and have enough time for Neri to speak about SUBRE, which is very important, I would say that the value proposition that we're trying to pitch today here with the building block approach of the Aspiral Flex product line is the modularity in it. As you could see, the fact that we're building those blocks in certified containers, even though they're water tanks, allows that you could move these things. So these are great for temporary installations. We have a couple of clients that are utilizing those systems as mobile units, actually. You don't have to build everything at one go. In other words, you can build it as you grow. One thing that we're seeing is that, for example, many developers, they would start off with having 100,000 gallons per day worth of wastewater, but they know that in the next 5 years, as their development, as they sell more lots and more people are going to come and live in that development, very quickly from 100,000 gallons per day, this application is going to turn into a half MGD application. Now, what is interesting is that you can start off with your first phase to use as those above ground package plants that you're seeing on the right hand side, but you can then still utilize, for example, the MBR building blocks and switch the biological reactors to become concrete basins, because you cannot build a city of containers. This is not what we're suggesting. I think that as I'm showing at the bottom bullet point here, these are very relevant for applications up to a quarter of an MGD. You could still use these for larger applications, but then it starts, to become many tanks, and I'm not sure that that's the most elegant and cost-effective solution. But up to a quarter of an MGD, we see it's a very competitive solution. Now, the MBR containers that I've shown here, for example, each one of those can treat 200,000 gallons per day. So a few of our developers or clients who work for developers, they say, look, why don't we use these MBRs for the entire half an MGD? Because it only calls for 3 of such tanks. And after the first phase of the 100,000 gallons, we can switch from biological reactor in containerized form to concrete. And then Fluence can either work with that client on leasing those biological reactor for the first phase, and only the second phase, Fluence will take it away and then offer our SUBRE towers, which Neri will talk about. So it allows for a lot of flexibility. I'm hoping that point is coming across clearly. And as I said before, the containerized structure allows for low shipping cost and low installation cost. Everything is, let's stick to that. The fact that these are all pre-engineered, that means that everything is factory tested. All of the work has done its work in easy conditions or comfortable conditions. And then when it's shipped to site, the only thing is that you need to interconnect between the tanks, which makes the labor on field extremely easy and much shorter. No build welding on site or anything like that. That reduces the cost on labor, but also the amount of engineering that needs to be put into a project has been reduced significantly, because from our standpoint, we don't need to charge a lot for engineering because the design for these tanks is already done, which means that now if I have an application, for us to design something is very quickly. We don't need to spend a lot of engineering hours. And then when we need to execute it, our builders, the people who actually manufacture these tanks, they don't need to invent the wheel every time because they have drawings. Those drawings are generic. It's very quickly. And so for us to manufacture these solutions and to engineer them, we were able to reduce the amount of time that we put into that, which is being carried over to the end client because we don't need to charge as much for engineering as others who need to customize every time the solution. Okay. The last bullet point is the flexible design. So as you could see, it could be tied into an existing facility, whether this facility is an existing package plant or this facility is an existing lagoon or lagoon municipal or an existing municipal plant. We could tie into any of it depending on the needs and the drivers. And we have the building blocks as our tools to tackle a specific need a plant has and not try to convert it into our plant all of a sudden. As you could already understand, the building block allows us to accommodate different treatment processes. So very easily, I could show you how we are able to couple the MABR with a UF membrane and call it an MBR plant. We could couple the Aspiral unit with a secondary clarifier and call it conventional activated sludge process. Or we could just do no MABR, because not if an application doesn't need the MABR technology. In other words, they don't need to remove nitrogen. There's no need for the value that MABR brings to the table. Fluence can always utilize these building blocks without any MABR towers and just offer a conventional activated sludge process or conventional MBR process. And as I explained before, this is really relevant for application up to a quarter of an MGD. It is feasible to treat more than that with these type of solutions, but it becomes many containers, and you really need to make sure that it addresses the drivers of the application. I will now hand it over to Neri, which will provide some update about our SUBRE product line, which is basically unlike the Aspiral package plants, which were providing the complete package plant. In the SUBRE, we're either retrofitting or doing green build for larger municipal plants, call it in the MGD flow range, where we're going to be utilizing probably concrete basins as opposed to an above ground steel tanks. So Neri, take it away. Thank you.
Thank you, Ronen, for your part and your interesting and eye-opening insights. I will now, if you can hear me well, explain a little bit about SUBRE, how it's different from the Aspiral Flex, and not only in the term of flow rates. I will start with just quick introduction. We still use the same MABR, and as Renan said, it's now used for greenfield or brownfield and expansion of existing wastewater treatment plant using our MABR towers. The main purposes and drivers are enhancing nitrogen removal or increase wastewater treatment plant capacity in order to provide better effluent quality, or if you need to add some more capacity, and it can be both, by the way. SUBRE is a hybrid process made of attached grow biofilm, our MABR, and suspended activated sludge, which is mostly the usual process that most of you know. We're taking the advantages of each of the processes and combine them together. The installation happens in an existing basin, if this is an existing plant, or where it's supposed to be called anoxic basin. It's now not anymore called anoxic, it's called SUBRE basin. I will show some graphic in the next slide showing the entire process and key points in the process design. We already have seen that when we're upgrading or using our MABR SUBRE approach, we can reduce the energy consumption by 33% thanks to the efficient oxygen delivered to nitrifiers, and also the fact that the denitrification happens also in MABR basin. And not only that, the next basin after, which is aerobic, works in a much low DO. And I will speak a lot about it also in the next slide. And lastly, MABR is a robust flat sheet membrane design that can provide minimal maintenance and has very long life expectancy. As we see, we have plants that are running now for more than 7 years, and functioning very well. So, few words about SUBRE process design concepts, just to help you understand better what is it. So first is single pass hybrid process, and I mentioned that. Single pass meaning that we have only RAS coming on of the solid separation. It can be secondary clarifier or UF membrane, call it MBR, but we don't have any internal circulation. So once the mixed liquor comes to the anaerobic and past the whole bioreactor, it doesn't have to have any internal recirculation. 4 major stages that we have are the anaerobic, that's used for the biosorption of the BOD and also helps us to promote EBPR. The biosorption helps us to control the growth of an excessive biofilm on the MABR membrane and keep it in the right thickness without having membrane clogging by excessive biofilm. Then we have the MABR, which is anaerobic anoxic condition. By saying that, I mean the ORP is mostly below minus 70 millivolts, and we detect it in several pilots and approve that. The MABR capture 45% of the total reactor volume, the total bioreactor, depends on site's condition and the goals that we want to achieve. And lastly, we have the aerobic low DO chamber that removes simultaneously also total nitrogen and BOD in aerobic reactor, where the DO is less than 1 milligram per liter and around and depends in the reactor design. Walking below 1 milligram per liter of dissolved oxygen allow us to have simultaneous nitrification, denitrification, and polishing of the BOD also. And it's, even though there are some claims that walking below 1 cannot perform well, we do have that after inoculation time, the suspended growth functioning very well, and you will see a result from a running retrofitted plant soon. And lastly, we do have the solid separation, which is the secondary clarifier or MBR. The secondary clarifier can work with 4,000 milligram per liter of MLSS. MBR can work with up to 10,000 milligram per liter of MLSS and allow us to enjoy the benefit of the two conditions. And again, it's depend on the client's needs. I just want to mention again, make it clear, we have no internal nitrate circulation because it's a single pass, and the fact that we get our total nitrogen right at the end of the aerobic reactor, so no need to have more nitrate or denitrification process.
I will just add, Neri, that the fact that we're able to, that the MABR enables us to work at an aerobic volume later at less than 1 milligram per liter DO, that is direct energy saving right there, because your typical, call it activated sludge that we would retrofit, would be operating at approximately 3 milligrams per liter DO. And right there, dropping it from 3, from a plant that used to be operating at 3 milligrams per liter DO in its aerobic, now it's operating at 1 milligram per liter. That is right there a linear energy saving of 2/3 compared right there. So that's a huge saving. Just wanted to point that out, that the DO translate directly to energy saving.
What you're seeing here is MABR. It's the first MABR retrofitted plant in the world. It runs in Israel for now more than 4.5 years and get very good results. I want to demonstrate here all the value proposition of MABR SUBRE retrofit. In the first table, you can see the concentration, the original design influent concentration, COD, BOD, TSS, everything that was designed was put as a design for the permit of this plant. And you can see in the second row the discharge permit of this plant, the original discharge permit. The next row describes the measured influent that's coming into the plant in reality this year, 2023. You can
After
also
the retrofit.
after the retrofit, correct. In 2023 effluent after the retrofit, you can see the effluent concentration, and it's definitely below the design and discharge permit. And this is thanks to the MABR retrofit. Now, the second table shows us the original basis of design in terms of loading for BOD, COD, TSS. The second row in this table shows you what is the predicted increase in loading that this plant will be capable to treat, thanks for the upgrade and the retrofit by the SUBRE. You can see approximated 25% increase in the coming loading. Last row shows you the actual loading that's coming into the plant this year, translates to pounds per day. You can see in some parameters, such as the TKN, which is what we're looking for, and also the BOD, we almost reached the original basis of design, and sometimes even exceeded. But thanks for the MABR retrofit, we got we allowed this increase of loading. So another point to emphasize is that even though the loadings already achieved the basis of design, using MABR allowed us to get better effluent quality, even though we already in the basis of design loadings.
So just to try and explain something real quick, if that's okay, Neri, those values that you're seeing here are pounds per day that are going to be removed, right? So the original basis of design assumed a pounds per day removal of these values, right? We came in with the SUBRE and we said, look, with the SUBRE, the same infrastructure will now be able to remove this many pounds per day, okay? In reality, this is how much we're removing, and this is the effluent quality we're meeting, meaning we can definitely remove more pounds per day with the same given infrastructure. And just to elaborate, this retrofit involved the retrofit of 22 SUBRE T3 towers that are shown on the right side into the anoxic basin, converting the existing basin to a low DO basin, and canceling the internal nitrate circulation.
Okay, so to summary the Mayan to be retrofit, which is completed. This retrofit allowed the client to increase the coming flow in 25% from 2.6 mgd to 3.3 mgd. We already proved that we saved, we provided saving in the power consumption, around 33% less energy consumption, and it translates eventually to even more because we can increase the loading. We also, this plant, as I mentioned, is operating since July 19, and the F1 quality is very high, even compared to the permit, and generally PN of 10 in the effluent with ammonia of 6.5 is considered to be a good effluent. Here in the picture, by the way, you can see the installation of one of our retrofit phases. These are the anaerobic chamber. Here is the SUBRE chamber, and this is the aerobic low DO chamber. What you can see in here is the total inorganic concentration, considering nitrate and ammonia, that coming into the Mayan TV retrofit. You can see the total nitrogen removal through all stages. These are average results of the last 2 weeks of this September. And we can see that the raw wastewater that coming around 42, 43 milligram per liter are mixed and receive some mixed with the RAS and receive some additional ammonia from a side stream, and then we see this concentration coming into the anaerobic chamber in here. The differences between the anaerobic to the SUBRE tank is the SUBRE stage is contribute to 18.5 total nitrogen removal that performed by the SUBRE, and additional 66.5 in the total TIN removal contribute to the aerobic low DO. And again, you can see here that at this week or these 2 weeks, the total nitrogen, the total inorganic nitrogen was very low, around 7 milligram per liter of ammonia and nitrate. And it's really important to emphasize that the low DO of the aerobic basin work in 0.18 milligram of dissolved oxygen, and it's really low and helps a lot in saving oxygen and saving energy.
So I'll just explain. It seems like the SUBRE TIN reduction is not great, only 18.5%. But 2 things to note on this. First of all, the fact that the SUBRE in here enables to convert this basin to a low DO basin, which the main energy saving is right there. So the SUBRE is an enabler to operate at the low DO in your aerobic basin, as low as 0.18 milligram per liter, as Neri suggested. The other thing to explain is that we could potentially treat the whole thing, and Neri will touch on that in the next couple of slides, but we could potentially treat the entire thing with SUBRE towers. But obviously, a SUBRE tower is more expensive than a fine bubble diffuser. So the way that we approach these applications is that we're running a techno-economical analysis on any new retrofit application that comes our way, where we're trying to see at what point the nitrification rate with the MABR towers is going to be greater than a nitrification rate that you would get from a fine bubble diffuser. And that is a function of the temperature of the wastewater. It's a function of how deep the basin is, and so on. And basically what we're doing, we're deploying just enough MABR towers to knock down the TIN coming in, as long as the nitrification rate with an MABR tower is going to be faster than the nitrification rate you're going to get with a fine bubble diffuser. Once that balances out, meaning we've diluted the nitrification so much that now the nitrification rate on an MABR tower is going to be equivalent to the one with a fine bubble diffuser, we're switching to a fine bubble diffuser because obviously, again, that is cheaper. So that is how we do it. And this explanation is going to set the ground to explain why the new configuration of our MABR tower has a lot of value. So please, here we go, Neri.
So now, after understanding the SUBRE process, I want to share with you one of our new greatest news for this year, having a new SUBRE tower design. And you can see here on the left-hand side, the old configuration, a circular one, and oval one on the right-hand side. I will explain now what is the main drivers and the reasons to have this tower. So the drivers are to increase the impact of MABR as we realize what benefits do we have from having more membrane. The second one is to reduce the total bioreactor volume by using more MABR. I will demonstrate the effect in the next slides. And lastly, and I think most important, we try to improve the dollar per gallon rates that we providing by using more MABR towers. It pushed us to put more membrane in the same volume. On the upper table, you can see the old module or the old tower design, the circular one. And please note what is the net surface area and the practical packing density. Now, with the new oval tower, please pay attention to the net surface area, which increased in around 80%. And for the practical packing density, which increased in 35% approximately, just because of changing the geometry and allowing to put more membrane at smaller volume. This allows us to increase the amount of MABR that we put in a reactor and not increase the reactor volume. To understand that, we run some analysis. So I will try to explain it slowly. And what you see here is an output of our design model under two configurations. First, on the left is the circular old SUBRE T3. On the right side, this is the oval SUBRE T3, the new one. There is very critical point to see in here. This point shows you that, and I need to explain a little bit more about the graph. The y-axis is the percentage of the MABR that applied. On the left side axis is the total reactor volume. The y-axis on the right side is the percentage of total nitrogen removed by the MABR. You can see that the more you put more MABR, you remove more total nitrogen. But in some cases, you slightly increase the volume of the total reactor. At some point, because of what Ronen just mentioned about the rates on the membrane, it's being less practical to add more membrane, because as you're adding more membrane, you're paying in more volume. So we optimize it up to this point where it's making no sense to add more MABR. This with the old configuration.
One second, Ari, just to explain. Obviously, an MABR tower occupies a lot of the water column, a lot of the basin volume, right? So if you put an MABR tower, you're basically taking a water volume that was going to be there. And so that's why you better compensate for it with a higher nitrification rate that you're getting with the MABR tower. And just to explain, with the circular model configuration, we saw that once we occupy about almost 40% of the basin, we're still at a higher nitrification rate with the MABR towers. But once we start occupying more of that basin with MABR towers, we're just literally increasing the basin size linear, and it's linear. So it doesn't make sense because you can achieve the same thing with fine bubble diffusers, right? But now, Neri, please go on what's happening with the new oval.
So the new oval here demonstrates, we modeled the new packing density and the same parameters, the same graph, but now with more dense membrane. You see the effect of having more MABR in a reactor. Now we flipped the trend, and we reducing the total volume up to the same point as here, where we slightly increase sometimes. Here we are decreasing total volume around 35% fill. We're starting to see that we are maintaining the same volume, more or less, and still getting very efficient total nitrogen performance. And the contribution of the MABR is more significant. And
now
just in the 60% of fill, you start to increase the total volume.
I will just say there's no such thing as decreasing the available infrastructure, right? The infrastructure exists, right? But what this graph shows you is that if you can achieve the same results, meet the same effluent requirements with less volume, what it means is that in reality, you can basically push more flow through that same given infrastructure. So we're not really going to reduce infrastructure. The idea is that this demonstrates that now with the new configuration, we can increase the flow that a given infrastructure can treat. If previously it was able to treat within 30, if you needed 36,000 cubic meter to treat a certain flow, now you can use the same, you have those 36,000 cubic meters and you can treat much more flow than you needed before. So we're not really going to shrink the size of an existing plant. We're just going to be enabled to process more flow through it.
This is where we are talking about a retrofit site. It will be applicable in greenfield site where your total volume will be reduced. So we both want to say thank you, and we have quick question time to answer. So we answered some of them on the chat, but feel free to reach directly to Ronen or to myself to discuss more of it. And thank you very much, Ronen.
Thank you, everyone. Again, I really appreciate your time. I'm also very proud to be right on time and not be respectful for your times. So good job, Larry. Again, you all have our emails here in the bottom of the screen. We're going to stick around a little longer. If anybody wants to ask any questions in real life, we're happy to address those as well. We did try to address most of the questions via the chat, but we'll hang on for another few more minutes if anybody is wanting to ask any questions while we are available. Thank you, Matt. Appreciate it. We'll put a face to. So just trying to address a couple more questions, CJ. I think so. Um, Addressing CK's question with having more than 300 installations, and that's a good comment to make. Fluence has over 350 operating MABR sites around the world. The challenges of expanding more in North America. North America, I would say, is the most conservative market in the world. Having installation outside of North America doesn't really satisfy some of the reference requirements that folks in US mainland would want to see. And so um, that's probably been the biggest challenge. That's honestly why we've taken on the approach of pushing very strong on our package systems that I presented in the beginning of the call, because it's a little easier to call it for someone to go after a small 10,000 gallons per day system without many references in the US, as opposed to an engineering firm and a client to enable a few MGD plant without any references in the US for such an order of magnitude. What we are seeing though is that the MABR is becoming more and more adopted by different cities and municipalities around the US. In 2024, we are expecting to have at least a couple of municipal jobs in the 1 to 2 MGD order of magnitude. So we are seeing that an increase in the deployment of MABR in North America. And I will say that up to date, we have approximately 15 operating plants in the US today with MABR. I think Sherry and Jessica addressed Kevin's question about the certificate, so please feel free to email those to us. And I'm seeing Neri is addressing, let's see. We'll go through some of the questions that we've addressed in the beginning for whoever is staying. Any issues with the container system being installed in cold weather climates? What we typically do, Paul, and it's good to see you. I don't know if you're still on, but on the containerized system, we can either insulate them with 2-inch fiberglass plates and trace heat the pipes. What we typically do in colder environments, we would bury the equalization tank in order to prevent the heat loss, and then maintain the process treatment above ground, either insulated or we put a small shed around it. But yeah, we do still require insulation, and we can support that effort. Recording should be available, and Jessica and Sherry should distribute the recording upon request. One second. Can the SUBRE model be applied to nitrogen removal for a complete recirculation of the liquid digestate and not just for wastewater treatment plant sludge? The answer is yes. We call it the nitro process. Nitro process is basically utilizing the MABR to tackle highly strength ammonia streams, just like digestate coming off an anaerobic digester or centrifuges. We're talking about ammonia concentrations up in the thousands, where what we're seeing is the process changes a little bit from nitrification, denitrification to what we refer to as nitritation, denitritation. I'm not going to go into this very much right now. Neri can take you through that, but we do have a product. It's called Nitro. We did not address it at this call, and we are actually actively looking to deploy a pilot for that product in the US. So very happy to discuss this. If you can tell us. I'm sorry if Maxim would love to talk about that if you have something in mind. Ramesh, are you having rising sludge issues in the clarifier due to anaerobic conditions? The answer is since the MABR is a champion in total nitrogen removal, we typically remove almost most of the total nitrogen at the prior to the solid liquid separation stage or the clarification stage, and so we're not getting undesired denitrification taking place in our clarifiers. So if anything, it's the opposite. The MABR actually enhances the performance of clarifiers because it's going to be very efficient at nitrogen removal, and it will prevent the development of nitrogen bubbles, undesired nitrogen bubbles due to undesired denitrification at the clarification stage. Paul, will this system be more effective in nitrification and denitrification at low temperatures near freezing? I will say that we use the same bugs. It's not like we have any special bugs in our process. I will say that biofilm bugs do tend to be a little more resilient when it comes to cold temperatures, but just like any other nitrifiers, denitrifiers, we do see a significant significant reduction in metabolism rate as the temperature drops. We don't like to go after applications which would have less than 8 degrees Celsius. I think it converts to mid 40s Fahrenheit temperature of wastewater, not ambient wastewater temperature, because just below that, the nitrification rate drops quite significantly. So those solutions would call for other considerations, just like, for example, I'm familiar with heat exchanging some of the wastewater to increase the temperature of the waste stream. But at the end of the day, yes, the biofilm does provide a little more resiliency to cold weather nitrification, denitrification, but at the end of the day, it's the same type of bacteria that does it, and its metabolic rate does slow down as the temperatures drops. What is the screening opening recommendation, and has it proven adequate in field? Any long-term fouling concern with the MABR modules? Regs, hair, grease, bio. Thank you, Simon. So not sure if you're still here, but I will say that at the moment we require 1.5 millimeter perforation fine screening ahead of the MABR process. We are hoping to be a little more lenient on that and bring it up to 2 to 2.5 millimeters, but at the moment we're at 1.5 perforated millimeters. That typically screens out all the hair and stuff like that because the perforation gives you another dimension of screening, and it's been proving very well. We use that. We supply our package plant with our own fine screens, which are very cost effective, and that alleviates some of the concern that some clients had, and we take responsibility for that. In terms of grease and oil, we don't have any issues with fog, fat, oil, and grease concentration up to 60 milligrams per liter to come into the process. It won't create any issues. If anything, the biofilm actually protects the membrane from these fat, oil, and greases. That's the good thing about having a biofilm growing on your membrane. I will say that if you are expecting like a small hotel or resort or restaurant to have higher fat, oil, and grease concentration, higher than 60 milligram per liter, that is, we would need to put a small grease trap ahead of it. About fouling, I can say that, as I said, we've had systems operating since, I would say, mid 2015, if you would. So we're already in the 8th year consecutive. We actually had system operating from before that, but we had never needed to replace a membrane throughout all of our 350 installations. Now, that's not because we're magicians, is just because if you think about it, the mechanism of the MABR is extremely simple. There are no moving parts, so there's no shaft or gears to be broken. Everything is made out of plastic, so nothing corrodes over time, which, sometimes plastic is good. And the pressure that operates against this membrane, again, I'm going to repeat that this is not a filtering membrane, right? So we're talking about less than 0.047 psi working against this membrane. That's it. Because we're not pushing air through this membrane, we're allowing oxygen to diffuse through it. So the pressure that works against the membrane is extremely low. So essentially, there's not much that can break. We don't need to chemically clean it because remember, the biofilm that grows on top of it is our treatment capacity, so we don't chemically clean. We just need to make sure that the application that we deploy these membranes in is the right application. So for example, we would never deploy an MABR process in brewery wastewater, which has only BOD, no nitrogen. If you would do that, then you would get heterotrophic biofilm growth on your membrane, which would clog the membrane. And that's why we would always only go after applications where there is a nitrogen component in the wastewater, which will promote the growth of nitrifiers, autotrophic nitrifiers on top of the membrane, which end up being very thin biofilm. So that's how we address the fouling. And as I explained, I should also say that Fluence is the only vendor out there that provides 15 years prorated warranty on the MABR towers. So we're willing to put our money where our mouth is. Neri, did you address? So there was a question. The system requires the 110:5 ratio of BOD nitrogen. What's the 5? Help me there. Is that phosphorus, Neri?
Yes.
So it's phosphorus. So the answer is yes. Again, we're not changing that. That's exactly why we need that ratio in order to promote the autotrophic nitrifiers to grow and not heterotrophic BOD removing bacteria to grow on top of the membrane. So Edgar again, now it's clear with the last clarification about the ammonia concentration. Thank you. Good. I think Neri answered Simon as well. Is it possible for the MABR system just in an existing wastewater treatment plant, for example, in a 20,000 people city? So, wow. So it's a Greek name. I apologize. I don't know how to pronounce it, but I encourage you to reach out to us and it's definitely 20,000 people. I'm assuming it's within the couple of MGD range, if I what is it, Neri? If you know that already?
What?
Yeah, it's 1.6 MGD. So it's in the 1.6 MGD. It's a classic application for us. So thank you. So as I said, it's a classic application. We would love to hear about it. This is exactly the type of applications that we're looking to go after, honestly. I think that answers all of the questions. And again, I encourage you, I will pull up just our emails one last time. If anybody does have any other questions, please email to either myself or Neri in these emails. You should have our Jessica and Sherry's contact information. So thank you so much again for everyone who stayed even longer after the webinar. We really appreciate your time. And we would love to hear from you. So thanks again, and have a great rest of your day or evening or morning. Thank you.
Thank you very much.